Welcome back to this Forge College Explainer. Today, we're really rolling up our sleeves and doing some serious engineering. We are architecting a continuous integration assembly line. Now, if you were with us for the last lesson, you know we mastered the art of manual debugging for Solana programs. Poking around, checking the logs, tracing transactions by hand. But today, we're graduating from the garage and building a fully automated factory. We're taking those manual skills and turning them into a strict, reproducible pipeline.
Okay, let's dive right into this. But it worked on my machine. Yes, it's probably the single most famous, or maybe infamous, excuse in the entire history of software engineering. And honestly, it's exactly why we need to make this shift. We can't just rely on tinkering in our comfortable, perfectly configured local environments anymore. We need a cold, calculating system that proves our Solana smart contracts work absolutely everywhere, not just on the specific laptop you happen to be coding on.
So, here's our blueprint for today's explainer. We're going to map out the jump from debugging to automation, lay down the 3 non-negotiable rules of CI, sketch out a 4-step pipeline, apply it to a real-world job, look at some AI prompts to speed things up, and finally, get ourselves ready for full network simulations. Let's get into it. Starting off with Section 1, shifting our mindset from manual debugging to full automation. You see, automation completely changes how you have to reason about failures in your programs. Manual debugging is, it's cozy, right? It's interactive. You can easily attach debuggers, pause the execution, and rerun a single file 20 times until it finally turns green. But CI automation, it's a completely different beast. It is entirely non-interactive and ephemeral. The machine spins up, runs your code, and then it dies. So you have to proactively configure an environment that captures failures perfectly without you even being in the room. That brings us to Section 2, the 3 rules of CI. To build this engineering marvel without wanting to pull your hair out, your pipeline must do 3 very specific things. First, reproducible environment provisioning. That means having the exact same versions of Rust, Anchor, and Solana every single run. Second, deterministic execution. And third, robust artifact collection. Literally, if you miss even one of these, your CI pipeline just degrades into an automated noise generator that pings you at 2 a.m. for absolutely no valid reason.
Now let's talk about deterministic execution, because this is a massive deal in Web3 development. If your tests rely on your local machine's system time, or if they're generating random keypairs that aren't properly seeded, your assembly line is going to break. It's that simple. Identical inputs must produce identical behavior across all runs. You have to totally control the inputs or mock them out, so the Solana virtual machine acts the exact same way, whether it's running on your local machine or on some server farm halfway across the world.
And think of robust artifact collection like investigating a crime scene. In CI, you can't interview the suspects. The code is not going to talk to you, and the server environment has already been destroyed. You're relying purely on the forensic evidence left behind. You absolutely need those transaction dumps, the IDLs, the target deploy folders, and the logs to piece together exactly what went wrong. If a job fails and you forgot to archive the logs, well, you've got a dead body and 0 clues. Don't be that detective.
Moving on to Section 3, let's sketch out the mechanical steps of this pipeline. These are the 4 concrete pieces inside a CI job that'll start the machines, run the quality assurance, and pack up the reports. Step 1. Set up your workspace and cache your dependencies so you aren't sitting around for an hour waiting for packages to download. Step 2. Build your Anchor programs and deploy them locally. Step 3. Manage the lifecycle of a headless validator, spinning it up and tearing it down. And finally, Step 4. Run your tests and, like a good forensic investigator, archive all those artifacts. Think of this schematic as your engineering master plan. It maps exactly which commands correspond to the specific forensic artifacts we need to collect at each stage. For the environment, we use commands like rustup and npm CI, and we save our log files and caches. For the build, it's anchor build, and we must grab the IDL and the program.so file. When we run the Solana test validator, we need its standard output. And for the tests, notice we run anchor test with the no capture flag. That is absolutely critical. It ensures standard output actually reaches your CI logs so you capture all those juicy transaction logs and stack traces.
Okay, Section 4. Let's look at a real-world CI job.
Let's take those blueprints and apply them to a real-world scenario, like a GitHub action. Treat this list as an atomic recipe. First, you check out the code and restore the cache. Next, and please pay attention to this one, install pinned toolchains. like explicitly stating Rust 1.69.0 and Anchor 0.27.0. If you just use the latest tag, I guarantee you're going to wake up to a broken pipeline because some tool updated overnight. Then we build, start our headless validator in the background, run our non-captured tests, and explicitly tell the CI to archive our logs if anything fails.
Now here is a super common, incredibly frustrating pitfall. You must explicitly wait for the headless validator to wake up and actually accept RPC connections before firing off your tests. If you just tell the validator to start and then instantly run your tests, your pipeline is going to crash on the spot because the validator is essentially still tying its shoes. You have to script a polling mechanism, like a loop running Solana ping 127.0.0.1/8899, so your tests only start when the local network is fully awake and ready to go.
All right, Section 5, AI prompts for fast CI.
Look, writing YAML files from scratch can be tedious. If you want to accelerate the construction of this pipeline, AI assistants are your best friend. First, feed the AI your repository layout and your exact commands. Be super specific. Second, adapt its generated YAML output. Never, ever trust it blindly. Always double-check the paths. And third, validate it locally using a tool like Act or Docker before you even think about committing it. Pushing broken YAML files 40 times in a row just to see if the CI finally passes is a rite of passage we can definitely skip.
So, iterate with small, precise prompts to ensure your pipeline script is rock solid. For example, if your AI-generated script misses that crucial validator wait time we just talked about, don't waste time rewriting it yourself. Just tell the AI, add a retriable wait loop for Solana test validator readiness with a 60-second timeout. Keep your prompts targeted like that, and you'll sketch out a bulletproof pipeline in minutes.
Finally, Section 6, getting ready for network simulations. As we wrap up our assembly line construction, let's review the core philosophy. Always treat CI as non-interactive debugging. Design your tests so they leave behind all the breadcrumbs you'll need. Second, keep your push-triggered CI incredibly fast. Focus on deterministic unit tests there, and save your massive multi-node network simulations for scheduled nightly pipelines. And of course, always automate that artifact capture for your post-mortem forensics.
And that brings us to a really compelling final thought. With your automated CI pipeline now acting as the rock-solid canonical invocation of your tests, how are you going to expand this script to orchestrate multi-node local network simulations? We are moving from a single factory line to an entire global supply chain. Well, that brings us to the end of this explainer. To answer that question and dive into advanced local network simulations, please visit forge.college to continue your Web3 journey. Thanks so much for joining me today, and happy building.